Subject for AP is ideal gas law, but I have to break this one down into a couple days because um, AP involves a lot of different calculations in with this one topic. So we're going to learn part of the calculations today and then work on more next lesson. So an ideal gas is going to be a perfect gas, which means it's hypothetical because most gases are going to get close to ideal but not be exactly truly ideal. So, in an ideal gas, molecules do not attract or repel each other. Well, we know that's not true because of intermolecular forces. They just have to be there. Even if the gases have broken those forces when they come into contact with each other, those forces are still going to exist. The other thing that is different is in ideal gas laws, they only have elastic collisions with each other in the sides of the container. And if you remember anything about energy, there is something called dissipated energy, in which if an object comes into contact with another surface, it dissipates some of its energy to that surface. So if I take like a rubber ball and drop it, it is not going to bounce as high up as it did initially for two reasons. Number one is it has to go against gravity as it bounces back up. And number two, because it dissipated some of its energy to the ground. It's not considered elastic. Trampolines have pretty close to elastic collisions. That's the reason you can keep jumping either at the same height or even a little bit higher each time because of the elastic collisions. The real gas molecules don't have perfect elastic collisions because they are going to dissipate some of their energy, especially when they bump into walls and containers. So ideal gas molecules, the other thing is that they do not actually take up space, which we know is not true because gas molecules have mass and volume and they do take up space. But some of our gases do get pretty close. So what we do is we use this calculation for ideal gas law to get an approximation of what we think could be a value that this situation could achieve. And it's always, our approximation is always going to be higher than what we can achieve because real gases do normal stuff like real gases do, like they dissipate some energy, they do take up space. They are going to have some attraction and repulsion within them. High pressure and low temperature cannot create an ideal gas, and we'll talk about that in another lesson. So this is the equation for ideal gas law. PV is equal to nRT, and the P is pressure. And I have on there, it really doesn't matter what unit your pressure unit is, but the problem is we are going to leave it only in ATM. We're not going to convert it to any other. We're going to convert all of our pressure units to ATM because AP's reference sheet only gives us the gas constant using ATM. There are other gas constants that use other units like kPa, millimeters mercury, but AP only gives us this one. So we're going to get comfortable with just using this one. Your volume in the ideal gas law must be in liters. Your N represents your moles, and it has to be in moles. So if they give it to you in grams, you have to do a basic gram to mole conversion. R is considered a gas constant, and it is a set number that we plug in. And this whole thing is the unit for it. I'll talk more about that whenever we start working out our problems. And temperature must be in the unit of Kelvin. Now, AP makes it a little bit easier, and they often give you the temperature in Kelvin. But if it doesn't give you the temperature in Kelvin, then you're going to do degrees Celsius plus 273. And that gives you your temperature in Kelvin. It's not degrees Kelvin, it's just Kelvin. And so we're going to work out some of these problems. You can solve for any of the variables other than R because R is the gas constant. The way that they find the gas constant is they actually go through and plug in all of these other variables for that gas at what we call STP, which is standard temperature and pressure. And that's how they determine this number. And so this number is a constant, and then we use it to solve for either pressure, volume, number of moles, or your temperature of a gas at a certain set of conditions. There's another equation. You're going to have a lot of problems throughout the year where you need to solve for molar mass. And molar mass is abbreviated as MM, and it is going to be in the units of grams per mole. And so sometimes we're going to have to solve for different problems using that concept of the fact that molar mass is grams per mole. Typically, when we talk about mass, we just do grams. But if I'm saying molar mass, it's actually grams per 1 mole. Density is mass divided by volume. And for the most part, AP is going to give you density in grams per liter. Now we need to list all of our diatomic elements because we're talking about gases again. So we need to know which elements are diatomic. So remember, we have hydrogen is diatomic. It would be the puck. If we're considering on the periodic table the hockey stick and the puck, it would be the puck. And then starting over on the right side, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those on the periodic table make up sort of looks like the number 7 or a hockey stick. So these are the hockey stick and hydrogen is the puck. Those are the only elements that are diatomic. These elements bonded themselves covalently to become stable. And so when we're talking about gases, we're always talking about them in this form. We're not saying that they're an atom of oxygen. We're always, if I say oxygen gas, I mean that it's O2. So let's go through and solve some of these problems. So it says, what pressure in atmospheres is exerted by 0.325 moles of hydrogen gas in a 4.08 liter container at 35 degrees Celsius? So I've got a lot of stuff given to me, and I need to make sure that I plug it into my equation the correct way. So again, my equation that I'm using for ideal gas law, and this is given to you on the AP reference sheet, is the PV is equal to nRT. So it says, what is the pressure? So that is my variable I'm solving for, so I'm going to just leave it as P. It tells me my volume is 4.08 liters. I know that is volume because the unit of liters is a volume unit, and in the ideal gas law, I must have it in liters. It gives me my number of moles, so I don't have to do any conversions. So my N is moles, so 0.325. My R is that gas constant. If we look back over here, it is this number here, the 0.08206 liters times atmospheres over mole times K. That is all the unit that goes with that. So what they do is at standard temperature pressure, they find and plug in the standard pressure, volume, number of moles, and your temperature, and they calculate it out, and they get this as your gas constant for atmospheres. And then my last thing is my temperature. It gives it to me in 35 degrees Celsius. That is not in the correct unit. And so I'm going to do 35 plus 273. I'm going to get that my temperature is 308 Kelvin. This unit, even though it's annoying to write out, is great to help you to figure out if you canceled everything right. So if I go through and cancel all the units that I see twice, I should have just one unit left if I'd set everything up right. And I do. So then we algebraically solve it. My variable is over here. So I'm going to multiply these numbers together and divide by the 4.08. Be careful when you plug these things into your calculator because your calculator works off of order of operations. If you plug it in the wrong order and it doesn't understand it, then it gives you the wrong answer. So we are going back to sig figs since we're doing math. So this has 3 sig figs, 3. We don't actually use this because it's a constant, 3. And so my final answer should have 3 sig figs. So it's going to be pressure is equal to 8.21. My unit is going to be whatever's left over, or if I think about pressure, it's going to be in atmospheres. So 8.21 atmospheres. Oh, hold on. I didn't do that right because I didn't divide by, I did all my multiplication. I did not divide by 4.08. So I multiplied these together and got the 8.21. I got to divide by the 4.08. So this is not right. My final answer is going to be actually 2.01 ATM. Next one, it says a 4.4 liter container holds 15.4 grams of oxygen at 22.55 degrees Celsius. What is the pressure in kPa? So We're going to change this to ATM because, like I said, AP actually doesn't give it to us in anything but ATM. So we're just going to say ATM. So again, my equation is PV is equal to nRT. So if I'm plugging in my pressure, that's what I'm solving for. So I'm going to leave it as P. That's not the only thing we can solve for, but that's one of the most common variables. My volume is 4.44 liters. My N is moles, and that's where I run into a problem because it doesn't give me moles, it gives me grams. And so I'm going to have to do a basic gram to mole conversion. So I have 15.4 grams. And when I say oxygen, I'm meaning diatomic oxygen, so O2. And then if I have grams of O2 here, I got to cancel with grams of O2 to 1 mole of O2. I'm going to find that from the periodic table. Each oxygen is 16, so 16 times 2 is 32. So then mathematically, I'm going to do 15.4 times 1 divided by 32. My sig figs come from my given, so the 15.4. So it comes out to 0.481 moles. So I'm going to plug that in for my number of moles. My R is the same R I used on the last one. And my temperature is given to me in 22.55. So again, I'm going to do 22.55 plus 273. I'm going to just round to a whole number to my ones place. So I'm going to get 296 Kelvin. It's technically, when I add it up, it's going to come out to 295.55. And technically that's what the sig figs would give us, but it's going to make your math faster if you round up here. So then I'm mathematically canceling liters and moles, Kelvin, Kelvin. I'm going to divide both sides by 4.44. So then I do 0.481 times 0.08206 times 296 equals, divided by 4.44. And I come out this time to 2.63 because I need 3 sig figs, 3 sig figs, 3 sig figs. And this one, I mean, right now I have it to 3 sig figs, but it would be different if I left it with the 0.55. And that's going to be ATM. This one's a little bit more complicated. It says a certain reaction occurs producing an oxide of nitrogen as a gas. It says the gas has a mass of 1.211 grams and occupies a volume of 677 milliliters. The temperature of the laboratory is 23 degrees Celsius and the air pressure is 0.987 atmospheres. Calculate the molar mass of the gas and deduce its formula. Assume the gas is ideal. By telling me the gas is ideal, it is telling me that I can use my PV is equal to nRT equation. So I'm going to plug in my information that I have into that. So I have 0.987 ATM times, so it gives me milliliters. You're going to have to convert that to liters. So to do that, I'm going to do 677 divided by 1,000 to get it into liters. And so it ends up being 0.677 liters equals, I'm solving for my N. I'm going to use my ideal gas constant. And my temperature, it tells me, is 23 degrees Celsius. So I got to do 23 plus 273 and comes out to 296 Kelvin. I'm going to run out of room over here. Okay, so then mathematically, I'm going to solve it out for that. So now I'm not solving for pressure because I won't always solve for pressure. It's just often we do. I'm actually solving for my moles. So mathematically, I got to solve this one different. For this one, I'm going to divide both sides, and I'm just going to use the numbers. I'm going to divide both sides by my R and my T. to be able to cancel it out from over here. So I'm going to do 0.987 times 0.677 divided by 0.08206 divided by 296. And I end up with my N being 0.0275. Will give me the correct number of units, sig figs. Okay, now I have my number of moles. It tells me that I've got to figure out the molar mass and its formula. Okay, so remember, molar mass is equal to grams over moles. It told me my number of grams. So I know that it's 1.211 grams. I just solved for my number of moles. So I'm going to work that out to figure out my molar mass. And it comes out to 44, I need 3 sig figs, so it comes out to 44.0 grams per mole. Okay, that is the molar mass. So then let me erase this down here so I can try to get the next part done. Okay, it says deduce its formula. So this is where you have to work out the problem. So we know that it's an oxide of nitrogen. That means that nitrogen is in this compound and oxygen. Okay, I'm just going to do the whole numbers to make math faster. So if I have 1 nitrogen and 1 oxygen, then my molar mass is going to be 14 plus 16, and that gives me that the molar mass is 30. That is not correct. Let's try it now with 2 nitrogens and 1 oxygen. So let's do the mass of 14 times 2 plus 16, and that gives me my mass is 44, which is what I have up there. Let's try one other option. Let's do 1 nitrogen and 2 oxygens. And that comes out to 46. So that is too high. This is too low, too high. So it ends up being N2O. And the way I know that is by process of elimination. If it tells you that you have an oxide of nitrogen, we know that it has these 2 elements in it. Okay, an oxide tells me that that is my second element in the compound. And so then you're going to plug it in and just start process of elimination, figuring out how many of each do I need. And so it is going to end up being N2O because it has a mass of 44, which is the same as my molar mass of this oxide. Last one, determine the density of ammonia gas at 0.913 atmospheres and 20 degrees Celsius, assuming the ammonia is ideal. So again, we are going to go through and figure out what my values are. So density is going to be D is equal to mass divided by volume. And in AP, it's almost always going to be grams per liter is going to be our mass and volume. So I'm going to have to go through and solve this problem out using the values that it gave me. If it doesn't give me some values, then I am going to have to make some assumptions. So for this one, I'm going to first figure out what my molar mass is of this substance. And this is NH3. So I'm going to take the mass of 1 nitrogen and 3 hydrogens. It comes out to 17.034 grams per mole. Then I'm going to do my ideal gas law. So I need to solve, I know my pressure, I need my volume. So right now my density, I know my grams, but I don't know my liters. So I'm going to have to solve for my volume here. We are going to use this, that it's this many grams in 1 mole. So we're actually going to use 1 mole as our number for our moles. And then I have my temperature is 20, but I won't leave it as 20. I'll add 293 or 273 to it to get 293. Again, I'm running out of room over here. Mathematically this time, I'm going to divide both sides by 0.913. Units-wise, my moles are going to cancel. Atmosphere is going to cancel. Kelvin's going to cancel. I'm going to be left with my liters. So I'm going to do 1 times 0.08206 times 293 equals, divided by 0.913 equals, I need 3 sig figs, so my volume is going to be equal to 26.7 liters. Oh, hold on, I typed in a wrong number there. I typed in 298. Comes out to 26.3. It's not a big deal. Let's say you made a mistake like that on the AP exam. If your chemistry is valid and somehow your calculations, you accidentally typed in a wrong number or something, they will typically still give you full points if you show your work. If I had no work here and gave an answer, they wouldn't give me any points. But they're pretty fair about there being issues sometimes with calculators. Like sometimes we type things in wrong, especially when you're stressed out on a test or fatigued from taking a long test. And so in those circumstances, they will be a little bit lenient as long as you show good chemistry. They'll give you points for it. So now I have 26.3 liters. So now I can plug it into this equation up here. So I'm going to do my grams, which was my 17.034. And that was in 1 mole. That's what I used down here. And that's going to go over 26.3 liters. And then I'm going to plug that in. And it comes out to 0.648 is what I end up with. And my unit will be gram per liter, which is a density unit. So again, a little bit more complicated, a lot of thought process through that to be able to solve that out. Next lesson, we're going to do some other calculations that have to do with the ideal gas law, where we might have to do another calculation for finding the total pressure of a situation before we plug it in. Big thing to remember is on the AP exam, they give you your ideal gas law equation. They give you this constant, and they actually give you this conversion here too. And so you just have to be able to use that information to solve out for whatever variable the problem is asking you to solve for.